So the living cell is actually a society of molecules. The human cell contains more protein than the United States has citizens, so there's quite a big society. And these proteins have to find each other and associate and act together. And in a very important way, the society is a society of blind entities. It's driven by random processes, by random walk. Nobody have eyes there. And still it works well. And that is a great mystery in a way, but we can answer it, but it's really quite amazing that we have living cells that work like Swiss watches, very quite precisely, and still they are based on random processes. Now, to drive this home, I might just take the example of two twins. They have the same genetic material, but when they, for example, get separated at birth, they really go to very different environments. They're subjected to completely different history of randomness in each case. But when you see them on the street and you put the same clothes on them, you might not be able to tell them apart. That would be the usual if they're single, if they're real if they are sort of like real pure twins. And so that tells you that nature can be very precise in some way, even though everything it does is based on randomness. And that is the subject that I want to talk about. Now you meet it anywhere, in every experiment you see the randomness. And so it's also very important if you want to understand and describe nature experimentally, theoretically. And once you get close, you see that randomness and you must be able to deal with it. And so that's what we want to do. And so we take actually a first process that is not random, and that is described by Newton's equation. And there we might have then one-dimensional motion that is described by a force F of Q, and this would be then the equation of motion. We would have to give Q at the initial point. We have to specify the velocity at the initial point, and then we can integrate it, and we are getting the famous laws of the planets and many other laws that we learned doing classical mechanics. Now, the molecules in the cell obey this law, but they are not like the planets in outer space, where they are very rarely bombarded by other planetary material. So they really go on a more or less pure orbit. But in the cell, we have these molecules that try to do their job in a condensed medium. And so if we just look at the whole thing, except for quantum effects, which can be important, particularly when you come to the electronic level, they obey classical physics. And when we simulate them in our huge computers here, blue waters with 100 million to 200 million atoms, for example, there's now a simulation running on the common cold flu virus. Over I think 240 million atoms, all classical. But if you would look at behavior, you find textbook example for statistical physics. You find the Maxwell velocity distribution being reproduced. You find the Boltzmann distribution being reproduced, even though the computer didn't know anything about it. The only thing the computer knew is the Newton's law. Now, if we, however, look at one particular molecule connected with such a system, for example, in the cell, there's a molecule that might happen to be not in a membrane or associated with some big cluster of other molecules, but just sort of swim by itself through the cytosol, which is the interior of the cell, made to some degree of water and ions, then we would see that it carried out a random motion. And that random motion has been described for a long time, and it is very well described by adding to this equation two phenomenological terms. So this is pure, no randomness. So this is a planet. And so we add two terms. One is minus gamma q dot, and force, this is a force and this must be also force, that is opposite to the velocity. So it always tries to slow things down. If we had only such a force, the system would come to standstill, and we know from Maxwell velocity distribution that if we have a velocity distribution for classical system of 0, that means that the system is at temperature T equals 0. Now that's not what the cell has, so we have also another force, an agitating force, that you need to add in order to get the temperature right. And this is written like this, where this is an amplitude. This here is called the friction constant or friction coefficient. So the magnitude is taken care of by the initial terms. Here we have an amplitude, and this one here is noise. And noise is actually a good mathematical term, and it just says that it's a random process. And this is equation. And this equation is called the Langevin equation. And this is all you need to know to describe now a particle that is subject to the influences of the environment. So you can go a little bit more fancy, like for example to say that these collisions are rather rare, so you have sometimes also ballistic motion possible. Ballistic motion is motion that is characterized by pure classical physics, just like a cannon shooting and a cannonball that you call a ballistic trajectory. So if you have something like this and the collisions are rather rare, you have to modify it a little, but not in the cell. In the cell the collisions are very frequent, and this is a very good equation. We can really live with it. We don't need to improve on it further. At least for a deeper understanding. And in my whole research, where I used this equation many times over, I was never asked by any referee, "Oh, you didn't use the right equation. You have to become more fancy." Okay, so this is the equation, the Langevin equation. And I told you already that there is a relationship between the terms. If we have only this term, we would have a situation where we go to temperature 0. This one adds noise so that we get a finite temperature. It turns out that these two terms, and we will derive that briefly without really deriving it, that they are related. So this one you call the friction, the frictional force. And this one here we call the fluctuating force. So they're both forces. And so they're related to each other by an identity which reads as follows: 2 kBt, the Boltzmann constant time temperature times gamma. So you see that, that you really have not two independent parameters characterizing the randomness, but only one, because of this relationship. This relationship is very deep. It is called the fluctuation dissipation theorem. Maybe, sorry, frictional, you also call it dissipative forces. I should have written here dissipative. So frictional is totally fine, but if you want to be fancy, you call it a dissipative force. So this is then the fluctuation dissipation theorem, and that holds, you know, that this is a phenomenological description of this kind of systems, and so it's not like the laws of physics in that sense, a law, but or a mathematical theorem, but it is for all practical purposes the theorem. So they are not independent of each other. So you have one term appearing in two. You have two terms, but appearing as two, but they are really one magnitude that determines the randomness of the process. So probably most of you have described a system that is governed by the Langevin equation, and so we want to remind ourselves of what we sort of know already from undergraduate physics, and so we're looking at the Langevin equation for the harmonic oscillator. In this case, the force is minus m omega 0 q squared, a q. That's a restoring force, a linear restoring force, and that characterizes the, except this omega 0 squared. Sorry. So this characterizes the harmonic oscillator. And so if we now solve the equation, then we have to solve the equation m q double dot of t is equal to minus m omega 0 squared q of t minus gamma q dot of t plus sigma psi of t. And now this is an equation where this is a left-hand side is determined by what's on the right-hand side. And the right-hand side, we have the independent variable q. Then when we know q, of course, we know also then the velocity q dot. And so it's all very deterministic here. But here, we have a random term. And so this one here is actually now a random process, because it is a solution of a, you call this a stochastic differential equation, where we have on the right-hand side a stochastic input. And so what is then coming out on the left side as a solution is also stochastic. But the moment we consider only the average of Q. So we are not interested in the distribution and any particular value today and tomorrow, but we just would like to know the average. So we take the average here, and then it reads as follows. When you take the average is a linear operation. So the average here, since we have time, it's not the time average. Time is a variable here, so we cannot just average over time. That would be crazy. But we say we have many Langevin particles, identical Langevin particles. Let's say an Avogadro number, 10 to the 23 particles. And now we average over all of these to 10 to the 23. And so then, Q of T average is then sum over 1 over n Avogadro, for example, J, and then Q J of T. So that is our average. And so if we do this, then we have on the left-hand side our average, but you can see quickly when you take here the first derivative, you get here the first derivative. You take the second derivative, you're getting the second derivative, and so on. So the average is not altered by taking a time derivative, and so we're getting it straight here for the second time derivative. Here we are getting it just for the first time derivative. Sorry, not for the first time, for Q. Here we're getting it for the velocity. And here we're getting plus sigma, and now we're getting the average over the noise. Now the noise, we don't know really what the noise is, but if I tell you now that the noise is actually defined phenomenologically, and one finds that the average of the noise is 0, that means a particle gets kicked by other particles, but it gets kicked as often from the left side as it gets kicked from the right side, and from the top and the bottom, and from the front and the back, then this averages out. And so we don't have that term anymore. And so then we have only this term, the other terms. And so then we have to solve the equation Q double dot of T is equal to minus omega 0 squared. Or maybe I just leave the m here, just leave it, you don't write it. Okay, so now we want to solve it. And the way we solve it is that we go and make a Laplace transform. So we solve the equation for Q hat of omega rather than Q hat of T. And so this is then given by dt e to the minus omega t from 0 to infinity times Q of T. So we take the Laplace transform of Q of T average. So if we do this, then we can also ask ourselves, what is the Laplace transform of Q dot of omega? And if we do this, then we find that is we can use the integration by parts, and we find this is e to the minus omega t times Q of T from infinity, from 0 to infinity, minus the time derivative of this guy, which is of course plus omega integral 0 to infinity dt e to the minus omega t, and now the time derivative of this fellow, Q dot of T. Now here we are getting at infinity 0, and at 0 this becomes 0, Q of 0 is 0, the average position in an harmonic oscillator that we have defined through this restoring force with a minimum at 0 is 0. We know that, and so let's not play funny games here. We expect this, and so we know it's 0. And so then we have here that the equation that that we get here on the right side, omega times, sorry, here was not the time derivative. What am I doing? I did the time derivative here. Here was not the time derivative. My mistake. So I'm getting here omega times Q hat of omega. So I'm getting the Fourier transform for the time derivative by just multiplying the Laplace transform of Q by omega. And what we used there was that Q of 0 is 0. And so likewise, you can show that Q dot hat of omega is omega squared times Q of omega, using that Q dot of 0 is 0. So the velocity distribution is also 0 for an harmonic oscillator, also for obvious symmetry reasons. So then we have the following equation. We have then omega squared Q hat of omega is equal to minus m omega 0 squared Q hat of omega minus gamma omega Q of omega. I left out something important. I would got a very, very boring result. So I have to go back. So here we solve this system, but if we don't do anything to the system, if we don't perturb it, then we are getting an equilibrated harmonic oscillator. The position will be 0, the velocity will be 0, nothing. But we assume we kick it. We kick it. And we kick it as follows, by adding here in our description a kick. And that's very, very critical. So we add a kick, and the kick is that we want to impart on the system a momentum P0. And you can do that by adding a term plus P0 times delta of t. So you know that you integrate over delta of t, that's a delta function, you get 1. And that's everywhere 0 except at t equals 0, you is not 0. And what you do is at this point is if you average over this force, you're getting a momentum. That means you're adding a momentum P0 to the system. And so that's what we do. And if we do this, then we have here in our equation plus P0, and now we have integral 0 to the t e minus omega t dt delta t is 1 times 1. The Laplace transform of the delta function is 1. And okay, that's what we get. If we didn't have it, then we would be not getting an interesting solution. Okay, so that's what we do. Okay, so now we bring everything to the left-hand side, and then we have on the left-hand side a factor Q of omega, and that everything else. So if this is Q of omega, this Q of omega, this Q of omega, we write the factor that is there. We divide the system through it, so we have then P0 over, and now M. So what I do is I divide the M out, and then we're getting here omega squared plus gamma over M. I divide out M, so this one doesn't have a factor M, so I have to divide them by M here, omega, and then plus omega 0 squared. That's what I get. And then P0 over M, don't forget the M here. And so now I need to solve this, and I solve it by the theorem of algebra, which was discovered by the very young Gauss. So Gauss was, a brilliant mathematician. The famous story is that when he was a little kid, the teacher wanted to keep the class busy and told the class, add up all the numbers from 1 to 100. And so he would have a little piece, and then little Gauss came after 10 seconds and gave him the answer. And he beat him up, but then it turned out that he was right. When the others gave in their numbers, teacher's pet, they got the same number. And what Gauss realized is that 1 plus 2 plus 3, 1 plus 100 is 101, 2 plus 99 is 101, 3 plus 98 is 101, so he knew 50 times I get 101, and that was the answer. And now then this guy, not much older, still I think not 20, he discovered the theorem of algebra. And when we apply it here, then he showed that we can write this one, but this holds for any polynomial. We can write this one as P0 over m divided by omega minus omega 1 times omega minus omega 2. So any polynomial can be written as a product of omega minus the zeroth of the polynomial. So omega 1 and omega 2, this of course we know from high school physics, from high school mathematics, is gamma over 2m squared minus omega 0 squared. So you have to use what you learned in high school and use it here. Okay, so that's what we get. And now this doesn't help us quite, but what we can do is we can write it as P0. We can write it as P0 over m times omega 1 minus omega 2 times 1 over omega minus omega 1 plus 1 over omega minus omega 2. So if you do this and then you expand, you put here in numerator and denominator omega minus omega 2 and here omega minus omega 1, you can very quickly prove it's right. So now these guys, however, are very nice because if we now go and do the reverse Laplace transform, then we find that these guys here are e to the omega 1t and e to the omega 2t. Just look up your mathematics book or derive it for yourself, and very straightforward. And so what we find then is that q of t, now we are going back to the t dependence, the reverse Laplace transform is equal to, so now we are doing another little definition. We call this square root omega, and we assume at the moment that gamma over 2m squared is larger than omega 0 squared. You can also done it without squaring it, but okay. So then we have here P0 over 2m omega, because omega 1 minus omega 2 is exactly this plus this. And this guy here is the same for both solutions. And then we have here e to the minus gamma t over 2m. And then we have here e to the omega, e to the omega t plus, I need a minus. Why don't I have a minus here? We have a plus, but now we get some more minus. Why do we get the minus? What is it? No, it is a plus. It is a plus, so it is a plus. So this is what it is. Okay, good. Okay, so this is a plus. Okay, now we know we use a 2 and this stuff there, and we can write then this one is V0. This is P0 over m, the velocity, and then times 1 over omega times e to the minus gamma t over 2m. times cos omega t. And if we are interested in the velocity, then we just have to take the time derivative. And if you take the time derivative, we are getting here sinh. And so then we're getting omega times, minus omega times sinh. So we're getting minus sinh and the omega in front. And so we're getting V0 times now the e to the minus gamma t over 2m, and then minus sinh. I might have made a mistake somewhere, but somehow. Okay, and now if we take the derivative here, then we are getting the gamma over 2m in front. And so then we're getting gamma over 2m omega times cos. So that's what I'm getting now, and I hope it's, I think that is what I get. So, okay.
Would there have to be a minus sign, otherwise the average of our position is not zero at time t equals zero? I mean, if there's not a minus e to the negative omega t.
Yeah, but that is the trick with the delta function. The delta function is really kicking in at t equals zero, just a little bit after the average, sort of. Just before it, we had the average zero, and then we are changing it. So up to that moment, it was correct. So I think that's what I get now. It's a little embarrassing. I don't want to be putting the wrong formula here, so let me quickly check it in my notes. Yeah, it's correct. It's no, it's all the way around.
Before your reverse transform,
See, jerk. I have sinh in the front. Why? So I got the minus.
Transform, it should be 1 over omega minus omega 1 minus 1
Yeah,
over
yeah,
omega
that's what I need. So I need a minus here.
And it comes from before, right there should have been a minus sign in that.
Here, there should be a minus sign.
Otherwise it's...
So I quoted here, I just made I did you the wrong, yes, you are totally right. Otherwise it doesn't work. So if we put here now, let's do it quickly, the calculation, and we're getting omega minus omega 2 divided by omega minus omega 1 times omega minus omega 2. Okay, and then minus, and now we're getting here omega minus omega 1. Divided by omega minus omega 1 times omega minus omega 2. And now the omegas go out. And now we're getting then plus omega 1 minus omega 2. And that cancels it. We get a minus sign. Good, thank you. And now we're getting a minus here. Then we're getting a sinh here. Sorry. And now then we are getting, so now when we take the derivative of this guy, we're getting a cos here. So we're getting a cos there. Yes, and the omega disappears. And here we're getting a minus gamma over 2m omega times sinh. Okay, good. Okay, good. So if we plot this, then we find that this goes as follows. And this one is V0, let's say it was positive. Then we are getting 1 going down to negative and then coming back. And so we're getting not a real oscillation, but we're getting 1 zero crossing. But that can be at a value where the thing is already very, very small, so that it looks more like it just decays here if the gamma is a very small number. Okay, so this is how it goes, and this you call the overdamped harmonic oscillator. The overdamped case, that is where the damping, we assume this here this is overdamped, is very large, larger than the frequency. And if we have an underdamped, then we have gamma over 2m is smaller than omega 0. And then we are getting the same, except this one is now becomes I omega. So we have now omega goes to I times something something real. So you're getting here a minus sign, so you absorb it and into factor I, and then you are getting q dot of t is equal to just the same v0 e to the minus gamma t over 2m. And now, however, the whole thing, except you're getting cosine omega t minus gamma over 2m omega sine omega t. Okay, and if you calculate the spectrum of this one with the Fourier transform, you are getting something that looks like I of omega is equal to gamma over m times omega squared divided by omega minus omega 0, omega squared minus omega 0 squared squared plus gamma over m squared times omega squared. And this is the so-called Lorentz line. And this is actually what you measure in neutron scattering. So if you have such particles that have strong enough neutron scattering, like heavy ions, for example deuterium, then you can see it in neutron scattering, and you can pick up the value of gamma and omega 0, and it's a very famous experiment. Of course, if you have a bigger system, then you see the normal modes of the system, not just one harmonic mode, but rather, you have many harmonic modes, and you might get then several Lorentz lines corresponding to the key vibrations of the system. So this is, the known behavior. So you see that, looks like we are on the right territory. But now we need to take a turn and do this a little bit more systematically. So what you have been doing in the past is, solving like the Langevin equation for certain conditions, and maybe you encounter some other cases where in the physics class you were exposed to stochastic processes. Doesn't happen too often, and you did then some ad hoc treatment. But in biological physics, randomness is so important that we cannot allow ourselves this kind of, let's see the trick of the day, or which trick would help me now. Don't tell me anything systematic. I just would like to know which trick I should use now to get an answer. That's not good enough, because you have randomness everywhere, and you have to deal with it, and you better have a more general tool. Now, this is not a class, a theoretical physics class, so I cannot go too far, and so I will not go very far at all, but at least I want to tell you, just very briefly, I want to give you a glimpse of, how do you really do that systematically. And so now we take a picture of it. Do you have a camera? No?
No.
But that is not good. I give you my thing, but you know, like the other ones, they took pictures always, and they should have told you have to bring your phone or your camera to take pictures. You know, that is really the job of the teaching assistants and not of me. So tell the next round of people. So now, do you know how to do this with the iPhone?
Yes.
Okay, good. So no problem. We quickly see. If the iPhone, I have a new operating system, so you have to constantly unlock it. So if it locks quickly, give it to me and I unlock it quickly. So that here we have it, and now it has a new camera feature, and you just take it quickly. Okay, so that is then a moment where we can ask some questions. So this is a very, very important area of biological physics, but I cannot do justice to it. I'm not going to go in overdrive now. But you know that everything in the cell is blind. There are all these molecules doing wonderful things, but they don't have a clue where they really go. But randomness is being employed in a way in the cell that it actually gets things done anyway. So that is a very deep, how should I call it, sort of deep experience that evolution developed, that you can do a lot with random process. Actually, chemists do that all the time too, and one of our main results on Tuesday will be actually to describe how molecules engage in chemical reaction completely randomly. And they find each other in the test tube, and you know, how can you control it? You need a certain concentration that they don't have to look too much for other partners and so on. But then the cell knows this, and they control then that the concentration is high enough that these kind of things happen quickly. But anyway, you are done?
Yes.
Okay, good. Any question?
Well, where did the fluctuation dissipation theorem come from? Is that just?
It comes. We get it, and probably that's where it comes from. Also in general, we get it from saying that the solution of these, when we calculate actually the distribution of P of Q and not just an average value, then we should go to the Boltzmann distribution. Then it postulates that these equations lead you actually to thermal equilibrium at a certain temperature. And then you say, yes, they go, but I have to put a condition there. If I don't put the condition, no. But if I put this condition, then everything is good. And so it's quite amazing and very elegant actually, but that it works. But it's sort of like an addition. It's almost like gauge freedom in electromagnetism. You have to add a certain gauge. You could also use other type of solution, but now you have to use this kind of solution. Okay. Okay. So, so now we begin with random process, and so maybe I'll leave this here for a second, and because this one here is, we know it works, and if I now invent suddenly a new mathematical description, it better work for this case. And yes, it does. So, but this is not the best description, and so we are doing a little bit different one. And that's the following. So we use a certain general form of stochastic differential equation. So the equations that describe how processes take place are time-dependent processes. So we must have some kind of differential equation, but this differential equation has noise input, and so we have to describe then differential equations that have noise input. And now when you go to mathematics class on differential equation, there are many types of differential equations, and first order, second order, third order, and you name it. And we have to, select one standard one so that we can deal better. And we can do this actually. And the differential equation that we use is the following form, the standard form, that we have a vector x that describes our variables. And then we take the time derivative of that. So it can be a two-dimensional vector. In case actually that we make contact here, x has two components, one is q and one is q dot. And so we have, but we can have more variables. And now we write here then one term that depends on x, on all its components, and it's also in the same dimension as A. So if it's a two-dimensional vector, it's a force, so to speak, that pushes the system in two dimensions. And so this is literally a force, but not in the sense of a Newton equation, but in the sense of you see it there. And when you solve this equation, then if you have here a solution, let's say you at this moment here at t equals 0, and here is x1 and here is x2, then the equation will go in this direction. Why? Because the direction of A at this point here is exactly this direction. And the magnitude of A is so that you're making in dt a certain displacement. So this would be x of t, and this here would be x of t plus dt, of t plus delta t, and this one would be delta 8a of x of t times delta t. That would give you the displacement. So there's nothing special there, a very normal differential equation. Might be easy to solve, might be difficult to solve, but nothing surprising there. But now we have another term, and this term is B. This one is a matrix. It also can depend on x. And this one actually multiplies now a vector eta that I write here, but it's the same dimension as all the other ones. So this is a matrix, and this is eta. It's a vector of noise. So that is how it is. And so now we have, for example, two-dimensional equation. We have two noise sources, one for the first component, one for the second component. And now the two components feed into this tensor, because the first component noise can actually also affect the second component if B is a matrix that has off-diagonal elements, and the second noise component can also affect the first if B is a matrix that has non-zero off-diagonal elements. If B is a diagonal matrix, then only noise in one channel will only act on one channel, a noise in the other channel only act on the other channel. And so this is a form of the differential equation that we use. So now, very standard, and now it turns out we don't need much more for the typical description in biology. And so now when we go here and relate the two, then do they relate? And it turns out yes, they do. We choose for x the variable mq dot and mq. So this is our vector. And then we have here on the left-hand side, x dot is equal to mq double dot, and here we have mq dot. And now if we write this one as a vector, then mq double dot we know, this one is f of q minus gamma q dot. So this is the first term without the noise, and this mq dot is just actually our first component, so we can write here immediately x1. And here what we do is we replace this one by x2 divided by m, and this one here we replace by x1 divided by m. And so now we have here our term a of x1 and x2. So I will rewrite it in a second. Now we go here to the next term, and here it turns out we write here sigma 0, 0, 0, 0, and then here we have psi of t and 0. So here we have only one noise input, and the noise input acts on the first component. If you do this one, then you see that our first equation is mq double dot is equal to f of q minus gamma q dot plus sigma psi of t, just our Langevin equation. And the second one is totally trivial. mq dot is x1, that's how we defined it, and 0, 0, 0, 0. So this we can then compare, and we find that A in this case is equal to f of x2 over m minus gamma x1 over m, and the second component is x1. That's our A, and our B is the matrix sigma 0, 0, 0. So this is how it works. So now, that is the general theory, and now we have a little bit of a problem. The problem is that we want to systematically deal with this noise. So when you are doing this on the computer, what you do is you would call a random number generator. If I tell you what are the properties of the noise, you would know what kind of random number generator you would have to involve, and then you solve it. But then you're getting, you use it for one series of random numbers, you get one solution, then you use another series with another seed, you get another solution, you're getting all kinds of solutions. But you cannot make much sense of it, but we want to be systematic about it. And so we need to learn how to be systematic in characterizing this eta, and we need to then find out how can we describe the solution. And it turns out that for the eta of t, we have then eta j of t, one component. We can characterize it through a standard noise they're very easy to deal with mathematically, and it describes many, many situations. And the noise that we choose is white Gaussian noise. So if we choose this kind of noise, then we can actually make very systematic statements about the random process that is solving this stochastic differential equation. So why do I do it so complicated? I want to tell you that, if you go to condensed matter physics here, and you ask them what is really the most important concept or the general concept, they will probably tell you quantum physics. It's really true, you cannot do much good in condensed matter physics today if you don't know quantum physics. Crazy, you cannot. Now, if you would ask in biology is much broader, so you can probably not get a unique answer from the biologists, particularly many of them are not really that quantitative. They collect still leaves and count the petals of flowers or whatever. It's a very young science, but if you would ask somebody who is a little bit more of a thinker, then likely they would tell you, particularly if you ask them that question, that random processes are really at the basis of living systems. So there are other things too, like genetics. The genetic mechanisms are important. Evolution is important. That the genes are changing and mixing all the time. But they will also tell you that randomness is very important. So we have here an aspect that is very fundamental. Now in this lecture I cannot do justice really, but I have to tell you a little bit more the principal approach than if I just tell you, oh, we have one trick here, and there's one trick here, and that's how it works. Okay, so let's continue. And if you have Gaussian white noise, then it turns out that we can characterize it through two properties. And the first property is the average value of the noise. And usually you can shift it around. That doesn't really give you a difference. You choose 0, but you can also have a shifted noise. That wouldn't be a problem. Gaussian is often around 0, but then you have a Gaussian that's shifted, not a big deal. So usually you can just give the average value of this random number. And now, this is now, however, time average. So this is a time average. No. I mean, you can get it at the time average. I tell you just something about the time average in a second, but it's an average. I tell you in a second something about the time average. So this one, and then the second one is you compare two time points of your random process, but let's say of even two of them, one in the J's channel and once in the K's channel. And then you find that this one is equal to delta JK, so the noise that you start is independent from one channel to the next one. There's no correlation between the noises that if K would so here when J and K are not the same, the noise is 0. But so then we have, and then however we also have this very odd property that the noise immediately forgets what value it had. So if this one had at time t1 one value, you ask, oh, do you remember what value you had last time, just a little bit ago? No, total Alzheimer. No remembrance. So that is key, and you call these kind of processes Markov processes. They are processes where the random process doesn't have no memory of the past. Whatever randomness develops in the future is not determined by the past. It's not like I never won on the lottery, even though I tried 100 times. I must win tomorrow. It must be because randomness is fair, and there is no God in terms of this property. Nobody remembers how you were treated by the noise the other day. It just every time it's fresh. Okay, so, and you do not need more properties when you do Gaussian white noise. White you call it because the Fourier transform, this one is constant. That means every frequency is equally represented, just like white light at every frequency. We call it white noise because of this delta function. It's really a very, very quick loss of memory. We call it Gaussian because it is really Gaussian. If you want to generate it in the computer, you have to generate univariate Gaussian random numbers. In the magnitude of the noise is given here by the B matrix, and so the number there, eta, they are just totally normalized. the normalized Gaussian, that you call univariate, the normalized Gaussian distribution, and around 0. And when you take two numbers at different times, they're completely uncorrelated. Okay, this is really, really awful, complicated and deep. And, yes, it is. And what I don't tell you really requires, a lot of thinking, a lot of mathematics. Like, for example, I'm writing on a textbook on the subject, and the other day I found a little mistake, and I thought I can repair it. It took me over 30 pages to repair this little thing there in my notes, because these things are really not trivial. And okay, good. So there's a lot behind there. I don't want to tell you, it's really trivial Mickey Mouse, but you don't really need to know. The only thing you need to know now is the question you probably ask yourself if you would have time. I go a little fast with this material, but if I would just say, I have to take a phone call, and you would then think about what do we really want to know, you would probably say, what I want to know is, what is the value of x at time t in the distribution? How is this value distributed over time? What is the probability that I find a certain value of x at the time t? I don't want to know the detail. One time the random process goes like this, the next time it goes like this, the next time it goes like this, and then it goes like this. No. I just would like to know the probability that I find a particle. That I get certain values of x. That might be the position of a diffusing particle. It might be, whatever. Okay, and now some really incredible, strong mathematicians derived an equation. The equation is given by a fellow's name, the two fellows' name, one an electrical and an airplane engineer, and one a famous physicist Planck. It's called the Fokker-Planck equation. And but they are really not really the father of the equation in the sense that they didn't really derive the mathematical basis of it. But it's named after them, the Fokker-Planck equation. And that Fokker-Planck equation gives you the time evolution of this probability, so that you know what can I expect for x in the future, just on the probability. And now the equation reads as follows. It is minus sum over j, and then you have a dj, aj, a is a vector, so this is the jth component of the vector of x of t, and then let me do this one you thought of. And then plus 1/2 sum over j and k, and then dj, dk, and then you take the matrix B, can depend on x, so I don't write it here. Don't worry. I just take the matrix B. We know it can depend on the variable, and the transpose of the matrix, you multiply them together and take the matrix element jk, and so this is a factor in the differential equation, and then you act with all this stuff on your distribution P of x and t. Almost like a Schrödinger equation. You have a potential to energy term, and you have a second order derivative kinetic energy term. This is not like the Schrödinger equation, but it looks a little bit like it, and it's just like solving this kind of equation. And the mathematics is actually very closely related to the solution of the Schrödinger equation. So if you know to solve the Schrödinger equation, and with a little mathematical ingenuity that I can teach you in a few minutes, actually, you can use all that knowledge to solve this equation. Okay, so this is now the deep mathematics. So when we have now and a Langevin particle or many Langevin particles, they might interact with each other and do all kinds of things. We turn them into this kind of stochastic differential equation, and from that we get then the Fokker-Planck equation that describes as a probability distribution. Can I trust the professor? That is really important. Okay, now I tell you very quickly. We go back to our equation. mq double dot is equal to f of q minus gamma q dot. We go back to this equation plus sigma psi of t. And now what we do is we realize something that is that if you apply this one to molecule 4 times larger equal a picosecond equal 10 to the minus 12 seconds. So really, like for both times you are really interested in your experiments and stuff. Then it turns out that mq double dot is much smaller than gamma q dot. It's okay. So it turns out it's a little bit like the story of an ocean liner or a tanker. You know, when you have a tanker, you know, their behavior is very much determined by the mass. And you ask, for example, how long does it take a tanker who suddenly loses power and cannot run the engine, that it stops, and it takes about 20 minutes or half an hour. So if the captain suddenly loses power, and there's the land coming, and it will take still 15, 20, 25 minutes, nothing the captain can do. It just crashes there. So there's really, like, depends on how heavy things are, you're getting certain time frames. Now if you have this time frame here, we can neglect this. And so then you call this one the strong friction limit. And if we have the strong friction limit, then we can write our equation as follows. Gamma q dot is equal to f of q plus sigma psi of t. And so then let's be patient. And let's say at the moment we want to assume there is no force acting on the particle. It does free random motion. It's also called free diffusion. No, nothing acts on it. Then we have this equation. And if we are going to our equation, then we have A is equal 0, and B is just a 1-by-1 matrix is equal sigma. So if we now write our Fokker-Planck equation, then we are getting dt q, p of q and t is equal to, and then we have 0, and then we're getting 1/2. This one here is just no matrix, really, sigma squared. But we have to divide by gamma, because on the left side we don't have a coefficient in front of the x dot. So we divide by gamma. We are getting sigma squared over 2 gamma squared. And then we are getting, here we have only one coordinate, j, and k is always 1. We write it then as dq squared. And since we assume this one is independent of q, so it could depend on q, then we have to do a little different. Let's assume it's a constant, p of q and t. And if it's a 3-dimensional equation, a 3-dimensional particle, you can see quickly that you are getting 3 dimensions. And in this case, this one would become the Laplace operator. What is this? This is an Einstein diffusion equation. Einstein's by far most cited equation. So Einstein did a lot of stuff, but if you ask what is Einstein most famous for in terms of of citation, it's a diffusion equation, because every engineer, every chemist, all of them use it, whereas general relativity and special relativity is not so much used, so very, very much used. So we have the Einstein diffusion equation. That is the Fokker-Planck equation. So you see that very, very famous equation is just popping up very quickly from this mathematics. And so there are many kinds of scenarios. You do not only have particles that are force-free. The cell works a lot with dimensions to put things into higher dimensional space where you have to search more, or lower dimensional space where it's much easier to find things. And they use a lot of forces between particles to bring them, to pull them together, the blind guys, to get them doing things faster. So there's a lot of variation there, but this is a starting point. So now I'm really a little behind here, but let me at least do a little bit. So the solution of this equation is very famous. I will put it as a homework problem. You're doing it a little bit of homework problem. The first thing, actually it's in the notes. In the notes we derive for you the following, that if you are looking for the following, that what is the spread of the particle squared, how much of this particle spreads out in time when you start at the position 0. So this is a starting point. So let's say we have a long tube with water, and we put ink in here, a little drop of ink. We put it here, t equals 0. How does it spread out? Well, we ask first not exactly how the distribution is, but we ask first what is this average q of t minus q0 squared. You call it the mean square deviation. How is that spreading out? Then you're getting a very famous law. You're finding 2 dt, where d is that famous diffusion from Einstein diffusion equation that is here apparently. If you compare Einstein's paper with what we have here, this is 2 gamma squared. So these two terms in the Langevin equation, sigma and gamma, they come here and they act here. Now we know that sigma and gamma are not independent. We know that this guy is 2 kBt gamma. Then we know immediately that this guy is actually kBt over gamma. So, okay, but anyway, so we know this is what it is in 1 dimension. If you go to 2 dimension, it is 4 dt. If you go to 3 dimension, it is 6 dt. Very easy to derive, and you see actually the derivation in the notes that were already posted for you, and Wei was kindly putting them together. So you can derive it yourself. And now what is the solution here of this ink drop? Initially it is dt, it is d, p of x and t, p of q and t, and t equals 0. The distribution is delta q minus 0, delta q. It's all here. This we call 0. So this is initial. What is now the solution afterwards? So that solution is p of q and t is equal to 1 over square root of 4 pi dt times e to the minus x minus x0, which happens to be in this case 0, we start at 0, squared divided by 4 dt. This is a very famous diffusive spread, and you put it into this equation that we wrote there, the Einstein diffusion equation. You show it's a solution. Very easy to do. You do the time derivative on the left, you do the second derivative on the right, and you find out the terms just balance out completely. So you see that I summarize now that we started out with the Langevin equation, where we had the frictional term or the dissipative term and the fluctuating term, and those acting on the particle. And from the environment side, they give it some randomness. We solved it and found out just this famous equation that we knew already for the overdamped and underdamped harmonic oscillator. Okay, that's a typical using some kind of trick. And yes, no problem. But then I said, no, that's not how we can handle it. We have to be systematic, because randomness and stochastic processes are too fundamental, and we need to develop a little bit more sophistication. Then I told you how we do it. We have a standard form of a stochastic differential equation that you find, say, x dot is equal a plus b eta. And so that's what we use. We find we can write our Langevin equation in this form, so all very good. And then I told you that mathematicians worked on it very, very hard, some of the best of them. And they could actually derive from this equation, making certain assumptions about the noise, a very fundamental equation directly for the distribution of that x. Here I write it as q, but it could have also been x, for the distribution and how this distribution evolves in time. That's a Fokker-Planck equation. Sounds very fundamental. Yes, it is, because when we are taking the case that corresponds to free diffusion, we get the Einstein diffusion equation, one of the most famous equations all of mathematical science. And that's also a very, very fundamental equation in governing the characteristics, the processes in cells. Probably I could tell you that if you would ask, conceptually speaking, which equation is governing most of the behavior in the cell, probably you could easily make a case, the diffusion equation. Because everything is random, these things work, they don't look random. You don't look random to me, maybe once in a while, but usually it's fine. But inside you, everything is random. It's just amazing. And so that is why it is important that we get a little deeper view. So then we will be solving the diffusion equation for case 1 and 2 and 3 very quickly, and then we go to the case where we have a force acting on a particle that drives the system, and see what effect, what difference that makes. And if we then have a little time left, then we will be talking also a little bit about reaction kinetics and how that is being done, but I'm afraid we don't have the time for that. Because we have the last section for the class, we will talk about the neuron, to end up with something that's really close to real biological behavior in the truest sense of the word. Okay, thank you very much for your attention.